Well, happy Tuesday afternoon. We're starting a new unit today. This is our next to last one, yay, yay. Way the schedule works, it's gonna be a little bit longer. It's gonna be 4 days instead of 3. I'll bring up on that a little bit later. Before we get going, any questions? So I've got a couple of pre-analysis or pre-things besides the general. Part of the object lesson of the last assignment was to realize that any kind of times you're dealing with those numbers where there's so many zeros you can't even use them in exponential notation, it's hard to get actually good handles on those numbers. So you can see a lot of things around. So the idea was to try to get the number of zeros right, to find out if this thing that is, one of the largest man-made projects or person-made projects on the planet would be cost-effective or not. And then I think your analysis were pretty much online with that. I mean, there's numbers that you can throw around. The state's budget's $80 billion. The whole US budget's $6 trillion. So, when they talk about $1 trillion worth of damage per year for the next 100 years, that's real money. All right? So that's the bottom line of that. Any questions on the assignment or evaluation of the assignment? I thought they were good. We're getting where we want to be. We've moved out of the phase of figuring out how to satisfy answers. We're getting more into an analysis phase, which is really where we want to be. This is business of the marine ice sheet instability hypothesis, published yesterday, was yet another, the whole thing's going to disintegrate and we're going to be, it's unavoidable at this point, according to this analysis. Another modeling exercise. They talk about the ocean-driven melting, and they put it in a little larger perspective. Here's Thwaites Glacier that we've talked about, Pine Island Glacier. They're talking about a much larger area and the melting underneath it. Their modeling assessment came mostly from modeling the ocean currents, not necessarily the glacier dynamics. And if their melting is correct, then there are some implications for it. We don't have a lot of data on that. The modeling thing is a two-edged sword. The modeling is one of the only tools we have to ask questions like this, but on the other hand, if it's too far afield from reality, is it useful? There's a garbage in, garbage out computer axiom from way back. So a little bit to get a perspective on that, the actual homework assignment today will be you going online to a simple model and playing with it a little bit just to start getting in your hands the sense of it. The reality is that probably most of you have done a spreadsheet budget, your own personal budget or something like that, and you play around like I do with the numbers to make them match up. That's a modeling exercise. You want to adjust things around to figure out what's going on, what you can pay or not pay this month or that kind of thing. Modeling is the same thing. There's more physics necessarily involved and there's more variables involved, but this particular set of that model I don't know that much about other than some of the people that were reviewing it are not happy with it, but that's neither here nor there. As I said, we've got 2 sessions left. That's broken up. It gets a little crazy because we have a no reading day coming up and Thanksgiving coming up and then the end of the term. And this is always kind of an enigma. So what I visualize is we'll hit this long CO2 for the next, Monday, Thursday, Monday, 2 weeks. We'll be taking a break. We'll come back with a new topic. We take a break and we'll pull it all together and we'll end up classes before there will be no finals commitment, of course, because we'll be done by that. In a practical sense, your last assignment will probably be this one. Now, we'll scale, because there's 4 daily assignments, we'll scale them a little bit differently, and I don't remember how we've done it in the past, probably 20, 30, 30, 50 or something like that, but we'll figure that out. Any questions of where we're going? We're going to talk about carbon dioxide, greenhouse gas that gets all the press. We're going to talk about it being long. And what do I mean by it being long? Well, we have this I don't know what the word is. We have this prejudice, it's not quite the right word, but this preconceived idea that it's the only primary force of the current climate change. We don't have to debate that right here. What is, I think, informative for us to understand is that CO2 is one form of carbon and it moves through a cycle. It doesn't just show up in the air, atmospheric. That's a sort of a recent phenomenon. But over the geologic time, it has been around forever. It will continue to be around forever, basically. And so we might want to know, will the natural carbon cycle actually remove the excess carbon dioxide that we're putting into the atmosphere? Maybe yes, maybe no. If so, how long would it take? Is it something that we can rely on Mother Nature to work on for 100 years and it'll clean up the atmosphere after we change the introduction of fossil fuels, or is it a much longer time scale? Are there any side effects to having Mother Nature clean it up? These are kind of, they're not exactly rhetorical questions, they're practical questions, maybe not for us most in the day-to-day business, but it's not harmful to see that there's implications beyond this. So we're going to look at, again, with the theme of the class, geological past coupled with the current studies of the carbon cycle to find some answers to these questions, or at least to approximate these questions. What do we know about carbon dioxide? Besides it's a greenhouse gas.
It's the primary force of the current climate change.
That's what it says. Do you believe that? I mean, I put it on the notes, but no, I can sit there and crash that PowerPoint and type a bunch of other words up there too, right? It's not PowerPoint, but it's immaterial. And is that the impression you have?
Yeah.
Yeah, okay, that's fine. I think a lot of people have that impression. What do you know about carbon dioxide? More than you want to know.
Plants use it.
I'm sorry?
Plants use it. They take it in.
So I still can't hear.
Like some plants use it.
Plants use it, absolutely. So are you doing anything with carbon dioxide personally?
Like I breathe it out.
You breathe it out. So you produce it, the plants use it, and exchange it for oxygen, and there's a cycle right there. I mean, that's photosynthesis from high school biology, right? What do you want to know about carbon dioxide? Yeah.
What do I want to know?
Yeah. Inquiring minds want to know, right?
I guess how realistic a solution to carbon dioxide, like reducing carbon levels is.
I'm sorry? With solution, what do you mean by that?
To like reduce the amount of CO2 in the atmosphere. How realistic something like that is.
I think if I present this section right, you'll come to the realization, not very. How does that sound?
That's kind of what I would assume, yeah.
If I present it correctly. If I don't present it correctly, you might not come to that realization. Anybody else want to know anything generally about carbon dioxide before we get into some nitty-gritty? Like I said, we're going to talk about the carbon cycle. Carbon dioxide is a part of that. We've already talked about a little bit of its respiration properties. And then we're going to turn to the carbon cycle in a broader sense to model some of the other elements of it going around. And so we're going to talk about the carbon cycle. Geology likes to talk about these cycles. There's a water cycle, there's all kinds of them. We've seen these before. The carbon cycle, among other things, moves carbon dioxide between the ocean's atmosphere and the land. And one of the things you see here is that it is a cycle. And it has multiple pathways, back and forth, one way, one way. The answer to your question really is how fast can this one happen? No, excuse me, this one happen. How fast can you go from the atmosphere into here, into the oceans? And actually it's going to depend not just going into the oceans, how fast can the oceans move the carbon dioxide into the sediments? This takes a while, this takes longer. We'll get some real numbers on it later. It's the atmosphere position of the carbon dioxide because of the radiative forcing as a greenhouse gas. the presence of too much carbon dioxide, because it acts as an acid, can change the chemistry of the ocean a little bit. And therefore, there are implications about things that like to live in the ocean. And so it moves around, and this particular thing omits the example we just talked about, biota. I mean, you got plants, and you've got things that photosynthesize, and you've got things that do not. And that's not in this particular carbon cycle. A lot of these cycles have sort of degrees of detail, shall we say. So you could start off with like 4 main players here, and if you take home from this lesson that interaction, that's probably fine. We could go to a much more detailed thing, and it would be so confusing, it would be hard to say. And I think the next slide is something about that. No, carbon cycles, carbon dioxide have been around for a long time. We have 100 million years ago, we have today. We have the geologic names here, and then the notion that these are warmer periods of times and it's cool. And this last part of the last 65 million years is known as the Cenozoic. Don't care if you know that or not, but it's a time generally of cooling temperatures. So when they say things haven't been this warm or whatever for the last 50 or 60 million years, a lot of them are looking at this incident here, and that's one of the things that's the PETM, which we looked at a while ago. So here's this warm event, broadly speaking. This cooling effect is fine. Now, the other thing is on this, so there's the temperature ranges. The implication of it cooling is that we started with ice on the southern pole, got cold enough that ice came and went, then permanently there. Now we're in a phase, if it kept cooling, the ice that's on the northern hemisphere will come and go, would become permanent. I mean, that's a geologic timescale. So that shows you the planet's definitely cooling. The CO2 is a little more complex. It's not directly, there's not an absolute strong correlation of this and this, because there are many other players that take place. Largely circulation patterns, because you're talking timescales where the continents can move around, and we've mentioned that. But you see spikes and dips and valleys. And so you hear things like the carbon dioxide hasn't been at these levels in the last X number of years. And the green line is sort of an estimate of our approximate CO2, atmospheric CO2 level today. It's, on this graph, it's been at least 20 million years since it's been this high-ish. So not recently. But prior to that, it was always higher than it is today. So the planet can get along just fine with high CO2 levels. And they're even higher than that in some other times in the past. Okay, zooming in on what would have been, excuse me, zooming in on what would have been about this little part of the geologic record, and going from old to young, and this is more or less the last million years. This is the Ice Age cycles, and we've talked about those before. One of the things to emphasize here is that there's sort of a series of low carbon dioxide concentrations, and there's less well-defined upper levels of carbon dioxide concentration. They don't always come back to the same time. These are associated with the glacial cycles. Now, one of the interesting things in this perspective is this sharp line here that looks like the edge of the graph, but it's not. It's a continuation of this through 1960 and 2000. So there's a pretty significant departure over the last million years of the amount of carbon dioxide in the atmosphere. You can play the game with attributing it to what. At some point, this attribution has to be to use of fossil fuels. But it's this range of natural variability that gives us some lessons. I mean, why did it change that way? And it's a chicken and egg question, whether it's the temperature is cooling or which way do I want to say it? Is this carbon dioxide fluctuation driving the associations with the glacial cycles? Not entirely. It's a minor player in that. It's there, it's vacillating, it's fine. And then who knows what we're into here. So we got variations from the last 800,000 years. They're all in these kinds of numbers. Do you know what the carbon dioxide level might be today approximately?
Like
Okay.
400.
Four and change, yeah. Yeah, I think I have a graph in here, maybe the next slide, I think it's 416 or something. So what is that implication about the natural, at least in the last many years, implications of it for the natural variations? Articulate it. We're not in the natural variability, right? That making sense? Okay. All right. And I don't want to get too much into the detail of this because we're mostly worried about carbon dioxide here. And how do we know that graph does that? It turns out that if you want to talk about this, you have to go ice core records. They're not excruciatingly detailed in temporal resolution. Broad pattern right on. They track the CO2 that's in the ice crystals or among the ice crystals, and they can measure that. If you want a more detailed look at that, you look at somebody named Charles Keeling, who invented the way to actually capture enough atmospheric CO2 to measure reliably. Turns out it's quite a technological challenge. He did it, started it 60-something years ago. His son Ralph is now carrying on the work. It has to do, the reason that they sample where they do, which is on the top of a mountain in Hawaii, because that's where the air is clean and where the mixing of the atmosphere doesn't, it's a better representation of the whole atmosphere than you would get if you put it down here in the middle of a city someplace. The measurements actually have to do with some fancy crystal ball, and I don't know the nuts and bolts of it, but they take the clean samples from the air at Mauna Loa. They've been measuring it for a while, and we have really good insight. And one of the things, one of your assignments is to go look at this website, just look at his general information that's there, and I think the question actually asks, what do you find most interesting? It's kind of a nice mix of human interest stories and technical data. Here's the latest technical data as of this morning. This is since they began the record back in 1959, I think it is. And here's the CO2 levels, and we see that there's a rise. And then there's a big flashy thing I didn't copy that says 416 parts per million right now. What do you notice about this general rise?
It just keeps getting higher.
Gets higher and higher, that's right. Is there anything about it, the graph itself, though?
I don't know.
If this were a stock market price of your favorite stock, right? What would be happening to your bank account with all of this business? In general, it's going to grow. But what about this stuff?
They're like little fluctuations.
There's fluctuation. These fluctuations are actually, do they look like they're random or not so random?
It looks like a pattern.
Looks like a pattern. So if you had to budget on these, you might even predict the pattern and go someplace for it. Okay, so there's a general trend. We can argue about the actual slope. There's a couple different slopes to here. It's increasing in slope. These patterns I'd like to look at next, I think. This is today. This is the last year, 2 years, excuse me. So from November to last November to last November. So are we in one of those fluctuations? Are we in a high or a low?
Well, on the last slide with all the little up downs,
Yep.
it looked like there was 5 per 5 years was the scale in the
5
bottom.
you counted off 5 for 5 years. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5.
Made me think it might have been a seasonal change, and then when you blow it up like that, it appears to be lower or going lower in the summer months and then rising in the winter months.
So he's exactly right. There's some sort of seasonal pattern to this. When you blow it up, it gets a little messier. You're not gonna see, exact dollar amounts, but there's an up and a down. And how big is it? How much change in the CO2 is it over those? They are yearly.
5 to 10. parts per
Five,
million.
five-ish, maybe getting up onto 10, something like, not quite 10. Okay, so that's not a 400, that's not a big deal necessarily. But it's rising up and down, rather this is significantly different than others. Now he started talking about it being seasonal, and do you agree with that?
Yeah.
Okay, well now then we have to explain them why the thing might be changing in a systematic fashion. This, for natural processes, is pretty systematic. Why would it be going up and down, up and down? And he said something about these months are low, these months are high. He's right. What comes to mind? Click on the cord, that'll come to a lot of me. What comes to your mind about changes over the course of the year?
Like the plants using.
What about the plants?
The plants would need more like carbon dioxide in like the summer because they're like blooming and like growing.
Okay, I like the plants. Go ahead. I like the plants. I like the fact that they might change their usage in the season. I'm a little concerned that summertime is sort of one of the high things, but is that because that's just, the plants are just getting geared up?
Well, because it's higher in like the spring because the plants come back.
The spring is the time when the plants have been dormant, so they're not necessarily doing any, particularly if they drop their leaves. So in those times, the thing can, they drop their leaves, it can creep up, and then it'll creep back down. So she's right on tune with that's the explanation of the seasonal cycle. Now there's one problem with that, or there's one caveat to it. No, it's correct. What about the plants in the southern hemisphere? Their concept of what November is not that it's fall, that's summertime. Right? Yeah, it is right. So what does this signal tell us about the plants in the northern hemisphere versus the plants in the southern hemisphere?
They have like different life cycles.
They have different life cycles. Well, they're still seasonal. What do you think about the number of, what would you guess is the number of plants in the northern hemisphere versus the number of plants, land plants, in the southern hemisphere?
There aren't as many in the northern.
In which one?
And there aren't like as many in the northern because it's like cold. Or
In the southern. There's not as much land area in the southern hemisphere. It's mostly ocean. So there's, we've teased out part of the carbon cycle. We've looked at there's something going on biologically that's changing this thing 8 parts per million every year. They're superimposed on it something else. All right. Standing back, looking at a more detailed carbon cycle, and this is the one I'm going to be dealing with for this assignment. All right. We just talked about the plants, right? Land plants specifically. Where on this, where are the land plants? Let's find an arrow or something associated with the land plants. Can you do that?
By the river or on the mountain?
Excuse me?
By the river.
There's some here, there's
Yes.
some here.
Yes.
Now, these diagrams are set up to show us where carbon dioxide is going from and where it's showing up to. The arrows show what we call fluxes. And that's this concept. How much stuff is going and how fast is it going? The other concept that's big to get out of here is this notion of what they call pools. So if you take all of the land plants as a pool, that's the carbon producers. And so all the land plants, as he pointed out on different elevations here, are collectively giving up or absorbing CO2. Land plants are gonna give up or use up or yield carbon dioxide.
They are different in daytime and night. Like, I remember in daytime they just create more oxygen and absorb the carbon dioxide because the sun.
There's a daily cycle associated with,
Yeah.
because there's no sunshine, so there's no photosynthesis. There's no conversion of carbon to dioxide. So one of the things about this is it's talking about plant respiration. There's an arrow associated with plants. Is that photosynthesis?
I'm sorry, that arrow is,
There's an arrow from the plants up to the air. Is that right?
yes.
What's this arrow from the air down to the plants? That's photosynthesis right there. What this is telling me is the photosynthesis process is sucking 120, whatever these things are, out of the atmosphere to be used by the plants. So there's a flux, that number's a flux. Oh, excuse me. Yeah, that number's a flux. The reds are fluxes. Now, what it also says is that because of plant respiration, different process, some of this is going back up into the atmosphere. How much of it? All of it, half of it, 10% of it?
It's around 10% of it.
Excuse me?
It's around 10%.
Got 120 coming down, you got 60 going up, sort of half, right? So even though it's sucking out a lot, there's still, it's giving, that plants themselves are giving off that, largely plant decay, that kind of thing. All right. Lady with the black thingamabobby, yes. Another arrow on there. Let's look for, you like red or blue better?
Blue.
Okay, let's find a blue arrow on there and see if we can explain it. There's not as many blue arrows. Oh, wait a minute, there's one. Guess you're stuck with blue, all right. What are the pools? There's two pools there that are linked in some way, and then there's an arrow between them.
The fossil fuels are used for like, the industrial thing, and then those produce more carbon dioxide.
Well, this is a funky one. Fossil fuels is a general pool of CO2. That makes a lot of sense. And they're talking about it being a black blob. Do you know why they're talking about it being a black blob? Because fossil fuels are generally considered like oil, which is a black blob. So someplace in the Earth's crust, there's, stylistically at least, it's all over the place actually, concentrations of something. So this is the fossil fuel part of that, and that's the size of it, whatever these units are. Kind of boring. And they point out that because of extraction to power automobiles in the industry, we're extracting that too. All right? Who likes red? You like red? Neutral on red? Would you be willing to pick a red arrow though?
Yeah.
Pick one.
Burning fossil fuels?
Burning of fossil fuels, okay. And so, which way is that arrow from
Going
going
up into the air.
up into the atmosphere? So you're consuming it here, and you're taking it into the atmosphere. How big a number is that? Can you read those numbers?
9.3.
9.3, okay. We just talked about plants having 120 of these things, and this one's got less than 10. Is that a big deal? It's only 10. I mean, the plants have got 12 times that, or the plants photosynthesis are 12 times that. So if the only thing going on in this diagram were 10 going up into the air every year, and that's a rate, petagrams, these things are petagrams, and the only thing coming out were, and it was 120 coming out, what would be the concentration in the atmosphere after a year? 10 in, 120 out. You would keep losing it from the atmosphere. Right, and it turns out if you look at the atmosphere, though, there's 750 of them. So there's 750 stashed up there, and we're adding 10 more a year, but we're sucking out 120 a year. But then we're adding in 60 a year. You see where the math is going here? What we have to do to have a carbon cycle is have all of the arrows in consideration, in balance. Okay, so we could figure out the things, and if you talk, like if you look at the ocean, that's interesting. 90 go out every year, 92 go in. How long, if you just had that half of this thing, forget all the rest of this nonsense. You had 750 up here, you have 90 going out and 92 coming in, jumping way in back in the black. If you had 750, and what's the net, which way is it going, into the ocean or the atmosphere? But just consider that part of it.
1,500 years.
Excuse me?
1,500 years.
1,500 years. Why? How did you get to that number, please?
Well, it's 2 more going into the ocean every year.
A net of 2.
Oh wait, so I guess it's 750 divided by
325 or something. Yeah, okay. So that would mean that if we had nothing else going on by that, the ocean uptake would exceed the ocean exfoliation by 2 petagram tons a year, and that would remove the carbon dioxide in the atmosphere. Well, if that's the case, why are we so worried? Why is the carbon dioxide going up? I mean, we just saw that it was going up.
It's not the only variable.
Excuse me?
It's not the only variable.
Definitely not. Look at all the other arrows in here. So we got to add those up somehow. All right? So let's just look at it. So this could do this. This is a tour. Disforestation and land use. That's only good for 1. It's going that way. Volcanoes is a always touted as a natural source of CO2. It is. It's a 0.1 on average. A lot when it's happening, but on average, not a big player. Talk about 120 and 60. We have something called soil respiration. There's 2 respirations from the plant and the soils, although the biological activity in the soils are respirating, like we are respirating, and sending CO2 into the atmosphere. And we're kind of getting to, we're talking about several of these. Everybody happy to look at that. The assignment when you play modeling, you're going to look at this model, and you're going to look at these things, and you're going to tweak some knobs, and you're going to see how those things would change as a result of that. That's what we're going to do. The other thing to kind of keep in mind right here is that the ocean's actually divided into 2 pieces. And this one has 725 petatons. The upper ocean, surface ocean, about the same as in the atmosphere. The deep ocean, or the intermediate and the deep, and we've talked about those before, 37,000. So, you could ask the question, where's the biggest pool of carbon dioxide, biggest reservoir of carbon dioxide? Here's 37,000, well, there's 100,000, there's the winner. Fossil fuels are only 10, however, 5 to 10, they don't know the exact number. So there's carbon dioxide in other parts of the Earth's thing. This is the only part that we get extract from fossil fuels. That's why it's such a much smaller number than that. But this is a big player. And then you notice we talked about sediments. And there's the little sediments that going from the ocean into the sediments. That's a flux of carbon dioxide. Lady way back. Can you see that number? It's 0.01. Okay, so what does that imply from the ocean, deep ocean, which is a big pool, 0.01 going into the sediment? What's the significance of that?
It's
Not a lot, right? If you had nothing else going on and you wanted to drain all the CO2 out of here, it's thousands of years. Okay, good. Anything else on the carbon cycle for now? We're going to digress a little bit to more theoretical things and then come back to this. I think this just repeats I think we've gone through it pretty well. Okay, sidetrack for a moment to recognize that what we just saw as an overview, people would agree with. Nevertheless, this one's was 2 years old. A group studying the Pacific warm pools were concerned about the fluxes. Same thing we just were, but they were looking at it in a much more detailed perspective. And so they looked at the warm spot that was out off Western North America, and they looked at the carbon, not only on the temperature of the water, not only on the plan view, but over time and at depth. And so this is deeper in the ocean. You don't have any color changes down here, which means there's not much going on. You have reds that are warm. And this is a time from 94 to 96 and a depth in the ocean where it was warmer than normal. Here's another hot spot. Here's a cold spot, or cold time and position. So this thing evolves all over the place. They weren't worried about that as much as who are the critters living in that zone. And lots of critters, and this was the part of this flux. But these are things just in the ocean. And these are the difference. So there's 1, 2, 3, 4, 5 of these things, and they're all going back and forth and back. Do I care about the details? I can't pronounce the names of half of these things. I don't care about the details, I do care about the flux. But one of the things that they noticed was that these things are all interacting. Under normal conditions, they have a net CO2 in and maybe some CO2 out. But when it's warm, these things interact in a different way. Some of them increase their activity to their neighbors, the green lines. Some of them decrease their activity. Okay, so it quickly becomes an accounting nightmare, trying to figure out all the details of who's doing what. But the point is, it's a complex system. We need information like this to better understand where things could go and how they might, how conditions might change. The thing we talk about has no consideration of this scale of detail. But nevertheless, people are really worried about it. Anything more on this? Okay. I would encourage you, if you have a piece of paper and pencil, to drag it out. If not, if you have something that you can sketch on or draw some diagram on. One of your assignment questions has to do, we're going to draw these individually in class. We're going to draw some little sketches, and I'd like to see those for the assignment. So there's like 3 different sets of these. They're all going to be basically this one. There's 3 different bathtub models. 3, getting successively more complicated, and it would be nice to see your thinking on this. So we're going to take time to walk through this. All right, what these are the conceptual, what it calls the bathtub model. We're all familiar with the bathtub. It's a pool of water. We can mess around with the pool of that water in one of 2 ways. We can dump more water in, we can drain it out. Typically, if you're gonna use a bathtub, you shut the valve so nothing drains out, so there's an accumulation, fine. After you're through with your bath, you turn on this outlet and the water drains back out, and that's fine. Well, what would happen if you actually had the water coming in and the water draining out at the same time, at the same rate, same flux? Gentleman in red, way back up there. There's a water level. I'm gonna make a graph here. I wanna look at it over time, and if I have in and out the same, what's the water level gonna look like?
It's gonna stay equal.
It's gonna stay equal. And so this blue line is a reasonable representation of the change in water level over time. That's a question, does that make sense?
Yeah.
So schematically, what we just talked about in words, there's a graph for it. Okay? Now, they're subtle, but these arrows are the same size as are these arrows, but the size is different. Okay? So I'm going to do what? What's the implication of that for the bathroom? What do the bigger arrows mean?
Like more water in, more water out.
More water in, more water out. All right, so our electric bill, our water bill is gonna go up. Does the water level change? So we would draw a steady line there. And you could visualize that you could do there's infinite amount of adjustments of the valves in and out to keep the water level the same. The next thing is if we've kept this water coming in the same, but I adjust the drain out, what's the water line gonna do, right? So I'm going to keep the water level going in, the volume going in, the flux going in, but I'm gonna cut down on the amount going out. So how do we, and so we've gotta sketch something, right? Notion is it'll change, right? If the water in and the water out are balanced, it's gotta change, the water level has to change. Therefore, the stock of water, the volume of water has to change. And if it's in a fixed container, its level will change, reflecting that. So what I'm looking for is how that will change. And guess what? The next example is choke down the water coming in, open up the water going out, and see what it will do. All right. You should be able to, now with this by inspection, should be able to sketch those out. You know, what does it do? And because this is constant, they basically should be a straight line. Is that making sense to everybody? All right, everybody have a good idea of which way they want to draw their lines. All right, I'd like you to replicate some facsimile of this on your, upload it for one of the questions, I forget which number it is. So, principles here this is a representation of fluxes in, fluxes out, and the reservoir, and then the fact that we can track that over time. That's really what we want to do. Okay? You get those two? So what do you think? If I really want to play splish splash, which one of these do I want to do? I really want to get my rubber duckies going and get splish splashing going. Which one of these, which model do I want to do?
The third one.
Excuse me?
The third one.
This one. Why?
Because there's more coming in than going out.
A lot more. So I'm going to have a lot more water. So what is this line going to do after I've throttled this valve?
Increase.
It's going to go up. Everybody comfy? I'll walk through this one. Which way is it going to go?
Down,
Why?
because there's more water coming out.
There's a lot more water coming out. In this case, I could be running the water in all day. What's going to eventually happen to the level of this? This can accommodate anything that's coming in, and it's likewise going to drain this pool, right? I started with 50 gallons of water or whatever it is, and because this valve out is bigger than this valve, I'm gonna get 49, 48, 47, blah, 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 down to 0 gallons. I'm not gonna have my rubber duckies floating, they're gonna be stranded. Well, that's very important, you've got to know what the relative ratio of these things are if you wanna float your rubber duckies. Yes, sir?
For the third model, is there do we set a limit of it off the top?
If it reached the top?
Yeah. Do we set
Yeah,
a
okay,
limit?
so this is hypothetical, so it could reach the top and overflow. It would exceed the capacity of that particular bathtub, right? That's true. I'm not too worried about it, because I'm just trying to, I'm assuming that these pools could have infinite reservoirs, but I'm just trying to track what's actually there.
Okay.
So in practical sense, yes, the rubber duckies are gonna escape in this one.
So we just make assumption the top is limitless.
Let's make the assumption that the top is not an influence, correct?
Okay.
Good question. Okay, so everybody got the bathtub model 1. Ready for 2. Model 2, we're gonna change it up a little bit. Somebody came along, and you could be friend or foe, they have a bucket of cold water, and they're gonna dump it in. If they're friend, you might dump in a warm one. If they're not friends, they're gonna dump in a cold one. Doesn't matter the temperature. I've got the same configurations of the valves, right? But now I'm gonna catastrophically dump in a bucket of water, not related to the valves in or out. What do these lines look like? Might as well sketch them out right now, you don't have to do it later. I'm gonna read a drink of water while we're talking about water. Ooh. Bucket of water, dumped instantaneously for practical purposes. Easy to sketch these right out, huh? Got it all done?
No, I was thinking.
Wait a minute, so easy, you're gonna do it twice, cause it's fun or what?
No, I was waiting to go like up first. It's too much. Just goes out like that, right?
No, yes, right, no, that's exactly right.
For the first one.
Yes, that's exactly right. Anybody else like me to look at one of theirs to just to provide some feedback? Yeah. Yep. This would be straight, this would still be a straight line. I mean, that's just maybe the way you've drawn it, but basically, that offset does that. Anybody else want me to look at? Everybody got an answer? Easy peasy. The next one's gonna be harder, go figure. Bathtub Model 3 is miserable. You better have 2 in control before we're gonna dump the bucket in. Catastrophic one-shot deal. The reason that we're doing an exercise like this is we really want to, when we start studying more complex systems, we might want to have a working idea of what we think's going to happen. Then we can test it. Sometimes it works out, sometimes it doesn't. What we're going to do in the real world, we're going to put 6 or 8 different valves in here. And we're going to have those pipes go to another bathtub, and there's going to be a different amount of water in the other bathtub. once that gets beyond 2 or 3 bathtubs, it's almost impossible for the human mind to figure out what is there. Therefore, we would use a computer model to do that. The system that you're gonna look at has, I think, well, it has all those bathtubs that all those arrows that we had. So quite a few pipes and quite a few bathtubs. That's beyond most people's comprehension to do by inspection. They can do it. Anybody need any more time on this? We kind of good? Okay, so we dumped the back. All right. And we're gonna call that a slug. I'm gonna call the slug of water. Boom. Now, there's a principle in chemical and a lot of physical processes that basically says how fast something happens depends on the concentration of the particle or the density of the particle. And there's a complicated math formula for it. But the way to think of this is, let's go to a glass of water and let's put in some floating balls that are sort of there, and we want to see how they disperse. And the dispersion then will ultimately go to this, but how fast will the dispersion go? It turns out, because those things are cluttered together, they're going to move apart fast at the beginning, but the further apart they get, the less drive to be further apart, so the slower they're going to go. So the conceptual idea is that this is how fast they're moving, this is time, so to go from this concentrated state to this diffuse state, it's an exponential equation, but it's going to go from this, not like we drew the bucket from like a step or a fast up, but exponentially. And the exponential is buried in that. We call that technically the gradient. Not very mixed, it's going to be slow. It's almost mixed, it's going to be slow. Excuse me, not mixed, it's fast. Almost mixed, it's slow. Oftentimes, this is most important if you're going across the interface. Okay, so this is a diffusion example of a gradient. So gradient is the key word here, concentration. How fast the process operates depends on the gradient. So in our other model, we changed the spigot open or closed. Has nothing to do with it. What if we actually pushed the water through, and we pushed it harder if there was high water, but we pushed it less if there was low water? That's what we're going to do on the next one. Oh, look, here we are. So this is, the arrows are different. What this is saying, here's the water level over time, analogous to the diffusion going on. The water in is the same every time. The water out is different. The water out turns out, for some oddball reason, to be a function of how much water there is. In this case, the water in and the water out are the same. Somebody want to explain what's going on here to me, please? We're almost around the room. Must be time for you again. Yeah. So in this case, right, that's the case I picked, water coming in at a certain rate. The water level is lower, but what's happening to the rate of the drain?
It's increasing.
It increases for some reason. We don't have a physical reason for that, but that's the way it goes. Okay, so this increases the rate that it can drain. But what's overall happening to the water level?
It's decreasing.
It's decreasing. So how do we draw that in here? Before you had sort of a straight line. Now we're going to have to put an exponent of some kind into it. So the water level is going to go down, but it's going to go down in an exponential shape. fill in the blanks. This one clogged up. Can't get much water out. Once it gets down, I get to a balance point. Now I get where it's draining faster and yet faster yet. This is like your bank account gets hit because you've got compounding interest fees, because your credit card gets overbalanced, and then they charge you more, and then they charge you more. Well, it is, right? You only got so much a month you're going in, but the amount that you keep going out depends on how much you've got in the bank. Kind of backwards, you'd like to see interest, you'd like to see it come up, but this physical system is the other way. All right, so let's see if we can visualize it. You got answers? So this is the slides, right? So you have, this one's getting you a little,
Yeah, I don't know.
this is a little bit. Okay. She's got the right tool to play with. Slugs, there's the slugs. Okay. All right, so they all don't look the same though. We gotta put something different for each one. They might all be exponential. But would they be the same exponentialness? In other words, something, yeah. So we've got different curviness. I mean, that's not the technical term, but that's. It's a gradient. Technically, a gradient. Yeah, gradients? Yeah, they're probably. And it's, which way is it gonna be? It's gonna be curvy this way or curvy this way. Got more or less straight line.
Yeah.
Yeah. Okay, so you've got curviness, okay. Or is this curvy this way or curvy the other way? So that's your argument, right? Just pushing it down?
Yeah.
So it ends up less and less valuable. Is that right? Okay. You got curviness over here? Curvy, it's only curves. Alrighty, anybody need another minute or two on this? So look at that, we've done a couple of the homeworks already. Assignments, this is wonderful. All right, I'm gonna tidy up here pretty fast. I wanna go back to this system. I wanna talk about some of these flows are pretty linear. Some of them have this gradient component to them. And the model is exactly this. It's the same diagram that'll be on the web page. And look, there's the assignment. Isn't this wonderful? Go to the Keating curve, view all of it. It's interesting. What do you find most interesting? sketch the sketches you just made in class, upload them, put some words to them to show me you know what you're talking about and you just didn't copy the thing from somebody else. The part you haven't seen is this conceptual online model. And then here's some instructions about it. I'm going to go to the online model and maybe so here's a little introduction. There's the numbers that we're looking at. Here's the diagram, the source of the information. This is I think there's a fellow up at University of Chicago that developed this. And so this talks about the flux and the different things between them. And we have the map. We actually have, he's got equations in there if you want to see them. And we want to run the thing. The little home thing will always get you back here when you get lost. So, good. So a model map is this. This is the way the nuts and bolts come together. The flows, the regulator flows are these arrows. Here are the processes. Here are the stocks, the atmosphere, the ocean, the plants. It's a system called Stella, which is great for modeling. We don't necessarily need too much more about that. All right, so we want to model run it. Here's the place where you'll spend most of the time. It's going to run the model. We could get a table of data or we could plot it as a graph. And we're going to talk about the atmosphere, the oceans, the soils, the fossil fuels. Now, are those the fluxes or are those the pools? The atmosphere, the oceans, the soils, the fossil fuels, and the plants. Those are all the pools. They're where CO2 hangs out. What we're going to try to do is talk about the flux, say, between photosynthesis and plant respiration. These are plant fluxes. We could talk about the ocean fluxes. We could talk about basically the soil parts of it. So in other words, we can talk about this 4 or 5 different fluxes, but you've got to navigate between the screens. The calculations will give you all of them. I think there's only 3 pages. By the same token, you could just look at all of these at one time, or you could look at one of them individually. Okay? So let's, under the initial model conditions, here's the things that we can mess with. We're just going to run it, and we're going to see that the fossil fuels for this situation, so let's look at the purple, the ocean. And the ocean has that behavior. Petagrams of carbon keep going up over 500 years. For the soils under these conditions keep coming down to 0, and the plants come down to 0. So under this set of model conditions, we can interpret that behavior. We might look at just the atmosphere alone. This is sometimes simpler. There's the atmosphere trending down, the atmosphere of CO2. That's kind of what we're objecting for, or we're looking for, if we want to cleanse the Earth's atmosphere. In this particular case, however, they did it from 550 down to 425, which is not clearing it out entirely, it's taking it down, but something prevents it from going down below 725. I don't know the exact physics, we could look it up. But this means that if we did something like this, don't expect it to go any further than this. This activity would only take it down a little bit. Questions how to interpret this. You want to run through another example. First thing I would do is go ahead to the initial values. They'll tell you what they are. You could change them if you want to get sophisticated. You might not want to. You can go to the model run page, run the darn thing, and then spend some time examining the different fields. The ocean, the atmosphere is coming down only to a certain level, but the ocean, but the ocean, the deep ocean at least, went up. So one of the places that went is into the deep ocean. Again, 500 years out north. This is a relatively short geological time. These things, I'm more interested in you looking at it, maybe tweaking some of the values and seeing how it changes. And let's go back to the exact assignment. And the assignment basically says, pick 2 pools, describe how they evolve, and pick 2 fluxes, describe how that they change over that period of time. Your choice, you can monkey around with the values and see if that matters or not. So far, so good? Then let me suggest we adjourn, and we will reconvene on Thursday and talk about this.